In this video, we present the concept and results of our paper for Humanoids 2020, Multi-Fidelity Receding Horizon Planning for Multi-Contact Locomotion. When traversing uneven terrain, humans need to consider their future steps for choosing the best location and timing of the current step. Likewise, when planning multi-contact locomotion on uneven terrain, predicting a few steps ahead is necessary to guide the immediate actions. However, this gives rise to a high-dimensional and nonlinear problem, which makes its online computation challenging. To improve the computation efficiency, we propose to relax the model complexity along the look-ahead horizon. More specifically, we split the look-ahead horizon into execution horizon and prediction horizon. The execution horizon accurately plans the first step using a centroidal model with rectangular feet and optimizes contact timing. The prediction horizon predicts the steps in the far future with a simplified model. In particular, we focus on finding appropriate convex relaxations for the prediction horizon. This gives rise to a novel type of formulation for planning multi-contact motions on uneven terrain. We call this formulation as receding horizon planning with multiple levels of fidelity. Next, we introduce three candidates with different convex models employed in the prediction horizon. For the baseline, the centroidal model is employed to plan over the entire look-ahead horizon. For the first candidate, the prediction horizon only considers the linear center of mass dynamics, while keeping the rectangular foot assumption. Further, the contact timings are fixed. For the second candidate, the prediction horizon employs a convex relaxation which includes both the linear center of mass dynamics and a convex approximation of the angular momentum rate dynamics. Same as the first candidate, the robot foot remains rectangular, and the contact timings are fixed. For the third candidate, the prediction horizon considers the same convex relaxation of the second candidate, while switching the rectangular foot to single-point foot. This further reduces the dimensionality of the problem. To evaluate our approach, we use the baseline and three candidates to plan offline centroidal trajectories of the humanoid robot Talos in the scenarios shown in this slide. We validate the planned trajectories by tracking them with a whole-body inverse dynamics controller in simulation. Next, we present our experimental results grouped by scenarios, along with the computation time of the baseline and our candidates. For the up and downhill scenario, the baseline can generate trackable trajectories at the expense of large computation time. Candidate 1 fails to converge after a few planning cycles, no matter how many look-ahead steps are included in the prediction horizon. For candidate 2 and 3, the trajectories generated with one step look-ahead in the prediction horizon tend to exhibit jerky movements in our simulation, which causes tracking failures. However, candidate 2 and 3 can successfully generate trackable trajectories with 2 steps look-ahead or more in the prediction horizon, while having smaller computation time than the baseline. Similar results are obtained in V-shaped terrain as well, where the baseline always succeeds. The candidate 1 fails to converge. And candidate 2 and 3 with one step look ahead in the prediction horizon generate jerky motion or fail in our simulation. However, with 2 steps look ahead or more in the prediction horizon, the trajectories planned by candidate 2 and 3 can be successfully tracked in our simulation. In addition, the computation time of candidate 3 is smaller than the fastest of baseline. Next, we present the results for Rubbles. The baseline succeeds in this scenario, but with extensively large computation time. Candidate 1 fails to converge again. With one step look ahead in the prediction horizon, candidate 2 and 3 cannot generate trajectories that can be tracked by our whole-body inverse dynamics controller. However, candidate 2 and 3 with 2 steps look ahead in the prediction horizon generates trackable trajectories in a fraction of the computation time of the baseline. Based on the experimental result, we can make the following conclusions. First, the failure of candidate 1 suggests that considering angular dynamics in the prediction horizon is necessary. Second, candidate 2, which convexifies the centroidal model of the robot in the prediction horizon, is faster than the baseline. This indicates that the convexification in the prediction horizon can improve the computation time. Lastly, it is worth to note that, although our approach requires longer look-ahead to generate trackable trajectories, the candidate 3 is still faster than the fastest baseline. For more evaluations and discussions of our approach, we refer the audience to the paper. Thank you for watching.